Welcome everybody to this, our first review session from the CREDDS Summer School on Dynamically Deformed Solids. We're happy to once again welcome Dr. Lorin Benedict from Lawrence Livermore National Laboratory, who will review the two problems that you should have all received via email after his Monday lecture. So with that, I am going to hand it over to Lorin.
Okay. Okay, so can you see the slides? I should be in full screen mode, at least I am in my computer.
I can see them.
I can see it from my end.
Okay, so I'm going to start. So I gave two, this might be brief, I gave two problems for you that were more conceptual problems than anything else, but I like those kinds of problems. So the first problem that I gave you to chew on was show that there is a maximum compression ratio, so rho over rho naught, where rho naught would be the initial density of something before you shock it, and then rho is the final density after you've shocked it, attainable by subjecting a material to a single shock. And the hints that I gave you were, well, so to use this energy equation in the box on slide 27, I'll show that on the next slide, and then, or the one after. And so this is when we were talking about the Rankine-Hugoniot jump conditions. And then to think about the fact that when you shock something, it heats up, which I mentioned variously throughout my talk on Monday. And then also to think about what the ultimate high temperature equation of state is for a material. The idea being, or the implication being, that if you were to shock something with a really high pressure, it would get really hot. And then the equation of state of the material in that final shock state would be, and what I was getting you to try to say is that would be, the ultimate high pressure shock state would be a material that has an ideal gas equation of state associated with it. So that's an extreme case, but that's what we were looking for in this problem. And then I also prompted you to read up a bit on the Rankine-Hugoniot jump condition. And I've suggested that even the Wikipedia link that I've provided here would be a good place to start. That's not necessary for solving the problem, but, you know, at least for myself, I don't like to just apply equations if I don't know where they're coming from, because it's you know, you have to understand a little bit what the background is, of course. And so while the solution that I'm going to show you doesn't depend on the fact that you understand the derivation, I just wanted to make sure that you had seen the derivation at least once. As I mentioned in the talk, you know, when you shock a material, which is a shock, again, is a density wave that's moving faster than the speed of sound in the material, you create, at least ideally, this situation in which you have a wavefront where in front of the wavefront you have a completely pristine material where nothing as bad has happened to it, and it doesn't know that there is a pressure wave coming. That would be like to the right of this red wavefront. And then behind it, you have the shock state. And so if you look just before and just after that and draw some diagrams and use conservation of mass, linear momentum, and internal energy, you get these three equations. And I was mentioning the energy equation down there. So although this is done in terms of density, I'm going to do things in terms of volume in my solution to this problem. I also mentioned at another place of the talk that when you're in really, really high temperatures, the equation of state is the ideal gas equation of state, which I am embarrassed to say that in my initial version of the slides, I had the wrong expression for the pressure in there. I don't know what I was thinking, but I've corrected it here, and I think that Michael sent out a corrected set. So hopefully you use the corrected set. So here what I'm referring to is these equations in the green box here. So the energy would be per particle, let's say, would be 3/2 K Boltzmann times the temperature, and then the pressure would be K Boltzmann T over V, the usual ideal gas equation of state. So now let's go back to this Rankine-Hugoniot jump condition energy equation, which is the one that, if you see my cursor, is the one that I'm circling here. This is exactly the one that I had before when I had the picture of the shock running through the material, except now in terms of this being 1 over rho and rho naught and 1 over rho, I'm doing things in terms of volume. Okay, but again, so the picture here is that the quantities with the subscript 0 are the initial state of the material. So let's say that's just a chunk of copper in ambient pressure and temperature, okay? So in density, all right? So it occupies a certain volume V0, and it has a pressure P0, which is at 1 atmosphere in our case, and then has some internal energy that just comes from the chemical bonds and things that store the energy in the material. And then you imagine doing a single shock, which then takes you to a final state with the which now you have energy E, pressure P, and volume V. And let me just close my window here because I got a plane flying. Sorry for that. Just a second. Okay. Hopefully a little quieter. All right. So what I want to do now is I want to take the final state variables, energy and pressure, and I want to plug in for those the ideal gas. So I'm going to equation of state. So I'll just use 3/2 kT for energy and kT over V for the pressure. And again, I'm doing this because I'm assuming that, well, as you shock something really, really hard, then the temperature is going to get really high. And this is the absolute highest that, if the temperature is approaching infinity, the equation of state has to approach this. And so just to make things a little more general, just for fun, and so we don't have to carry around a bunch of numbers, let's make, I'm just going to replace the 3/2 by the number alpha and the 1 by the number beta, so we get a slightly more general solution so we can see what that looks like. And now let's plug in. I'm going to plug in the E alpha T equals beta T over V into the first equation up there. And so I get that. And now, of course, I want to solve for this compression ratio, which is V0 over V. That's the ratio of, how much a material is shrinking after I've shocked it once, okay? And so I've got to massage this equation into something that allows me to solve for V0 over V. And when I do that, I see that I get a quadratic equation, right? So here's the V, this is the term of squared, and that's the linear term, and that's the constant term. And so then I can use the quadratic equation to solve that. So I get this. Now, of course, as usual, I have my two roots. However, if I take the limit as t goes to infinity, so for instance, that means that this term, this beta t term, will end up outweighing the p naught v naught term, as an example. And if I use similar reasoning throughout, to take the limit as t gets very big, it turns out that the root that I get from the minus there in front of the square root, in the limit of t goes to infinity, that just becomes 0. So that's not the physical solution that I want to look for. So if I take the plus 1 and I take that limit, I get simply beta plus 2 alpha over beta. Okay, so that's what I get. And then if I plug back in for my 3/2 and my 1, I get 1 plus 3 over 1, which is 4. So this is something that you will hear a lot of shock physics people talking about, that you can only compress, by shocking a material once, you can at most compress it to 4 times its initial compression. Now, of course, that's not exactly true because, as you might imagine, a material doesn't just go to its, to its ideal gas equation of state, and that's it. I mean, you can actually shock to a lower pressure, have the thing heat a little less, but in fact dump more energy into things that don't just go into resisting compression, but go into breaking chemical bonds, for instance, if it's a complicated material. And then you can compress a little more. And so here's an example of that I just wanted to show you. This is from a paper that is soon to appear, like any day now, in Nature. The first author is Andrea Kreitzer, and I'm on it as an erstwhile theoretical contributor, and I believe Bruce Remington, who I think is also signed in, is also in it, and there's about 25 or 30 other people that are on it. So what they did here, or what we did, is at the National Ignition Facility, we took a ball of this particular material, which is a C9H10, so it's a plastic basically, and shocked it by having it undergo a spherical convergence, so the pressure gets very, very high, to really in the hundreds of megabars of pressure. So it's a very, very high pressure. And then when you do that, and so this is now this is now, you can actually, because of the spherical compression, it's possible in a given experiment to trace out a bunch of these final states, although traditionally, of course, as you can see for lower pressures here, each point would be a separate experiment where you shock and then you shock a little harder, and then you shock a little harder. And each one of these is a separate experiment, but because of various tricks of the experiment here, it's possible to trace out a curve. And so what Annie and company did was to do this for this material, and then she gets the red points, and then there's error bars in the compression ratio. This was another paper many of us were also on, also involving Dr. Kreitzer, but led by Thilo Deppner, where it was they did a similar thing, but just with a lower convergence. And so you trace out this pressure as a function of compression ratio, and as advertised, it goes through a maximum somewhere. And it turns out that the maximum here is, I can't say so experimentally because we haven't gone all the way up to infinite pressure, but there is the indication that, like the theories suggest, and the theories are here in the solid and the dot dash curves, it is expected indeed that you would go through a maximum, and that you can't just keep compressing forever if you shock a material just once, because again, you're heating, and the heating resists compression. And you notice that there's a bunch of these jogs, some of which are actually reflected, thankfully, in the experimental data. And these jogs to higher pressure or even lower pressure here, the shoulder over there that I'm showing you, and then this bump over there, that comes from the fact that what you're doing is, in this particular case, you're ionizing different shells of the carbon atom. So here is ionizing, I think, parts of the N equals 2 shell, and this would be ionizing some of the 1s squared electrons, so the most deeply bound electrons. And the point is that, okay, so when you shock, since that thing has internal structure, namely it's a bunch of carbon atoms, and the carbon atoms have electrons that are, tightly bound to it, then you're putting energy into that system. And let's say, for instance, that energy, some goodly amount of that energy goes into ionizing those electrons. Well, that is energy that does not get to be translated just into translational motion of these otherwise free particles. And so that's why you don't actually heat as much, and that's why you can compress a little more than 4 times. So that, what I'm trying to tell you here is that if the matter has some internal structure, and all matter does, it's not just billiard balls, right? Then of course, as you excite things in that and liberate those internal degrees of freedom, that allows you to compress a little more. But at least the theories show still be true to be verified by experiment. Once you do all of that liberating and you really start to increase the pressure even more, sure enough, you go to this magic answer of 4. So you can see here, at least in the theories, how I'm beginning to asymptote to the result that we derived by just plugging in the ideal gas equation of state, which is the 4-fold compression. Okay, I should also mention finally that you get this 4-fold compression answer when you don't include relativity. If you include relativity, as in special relativity, so now your equation of state is not the one that I've delineated, but the ideal gas equation of state for a relativistic gas is different. And that difference actually makes it so that now the ultimate compression is 7, not 4. So the way that at least the theory would predict, again, to be verified by experiment in the future, would be that it asymptotes to 4 here, like my cursor is showing, but then it takes another jog again and becomes 7. And that's not because you're liberating any other degrees of freedom. You're not, or anything like this. It's really just because the ideal gas relativistically is different than the ideal gas classically. Okay, second problem. So I asked you to use the concepts that we discussed in the lecture on Monday to explain, to the best of your abilities, the phenomenon of thermal expansion. So the hints I gave you were to consider a simple solid material to which one can employ the Mie-Gruneisen equation of state model, which I had described on the slide 49, which I will reproduce for you in a few minutes. And then to really try to understand exactly why it's thermal expansion rather than, for instance, thermal contraction as an example. What is it that's really, what is the major engine that is making materials want to expand if you heat them? And another bit of hint, I guess you could say, that I gave you was to note that the Mie-Gruneisen equation of state model that I presented was really presented in the context of me describing descriptions of the ionic excitation part of the free energy. Okay. And we have to also add on some cold piece, as I described before, in order to get the total free energy. And here I'm suggesting that you could just neglect the electron thermal term, since it's generally far smaller for most than the ion thermal term for most solids. So here was the slide that where I talked about the Mie-Gruneisen equation of state, here delineated by sub mg Mie-Gruneisen. And so it has a fairly simple form, and it involves this quantity theta, which is like a Debye temperature. It's a characteristic phonon temperature, which as you squeeze on a material, this gets larger, as I've indicated here. As volume goes down, then this characteristic energy or temperature, if you will, gets higher, which is basically just saying that if I take something which is a bunch of balls and springs, and I squeeze it, the spring constants, at least we know from experience, actually get higher. And so the characteristic frequency, square root of K over M, where M is the ionic mass, will get larger. And so that them getting larger means these frequencies start to go to a higher energy, which is what you see happening in this histogram or phonon density of states that I've plotted on the left. Okay, so that means that, well, the right thing to do would be to take some cold pressure, which is going to be some P naught of V, depends only on V because it has to do with just the squeezing the material at zero pressure, and add to that this ion thermal term, which has this form here, the P underscore mg, which would be 3 kT over V times some quantity gamma, which is called the Gruneisen parameter. And that Gruneisen parameter is related directly to the volume-dependent characteristic temperature theta, the Debye temperature, and it's related in the manner in which is shown in the bottom left of this slide. So it's the negative logarithmic derivative. So that means that the larger the slope of theta is, the more negative that slope is, which means that the more the characteristic vibrational frequency increases as you compress it, the larger and positive the Gruneisen parameter will be. Okay, so if I have that form, so then let's, so let's consider two temperatures, let's say a temperature 1 and temperature 2, and let's assume that temperature 2 is higher than temperature 1. Then let's write down the pressure of the material as a function of volume at T1, and then let's do it at T2. So if we do it at T1, I get this, here's my P naught of V, which is independent of, that's my temperature independent part of the equation of state, or the pressure equation of state. And then I have this term that comes from the Mie-Gruneisen model, and there's a T1 there. Okay, and I do the same thing at T2, and you'll get this. So you'll notice that the only dependence on T1 and T2 within this model is just right here, the thing that multiplies the gamma. The gamma doesn't depend on T. The P0 doesn't depend on T, so it's just this in the simplest description. So this is assuming, again, a quasi-harmonic framework, okay? And remember, of course, that we said that gamma is generally positive, and we talked about why it's positive. It's positive because it's the negative logarithmic derivative of this, and so that makes sense. It's basically a number, it's a unitless number, because it's a logarithmic derivative, that is measuring how much the vibrational energies increase when you squeeze something. That's what gamma is, okay? So if I have these two equations, let's plot them both as a function of V. Since the T1 I'm making blue and the T2 I'll make red, I'm gonna make those curves blue and red respectively. So here's my pressure as a function of V as a function, plotted here. And let me just draw illustratively a 1 atmosphere. So this is close to zero pressure. This is what you and I are experiencing being at ambient pressure here. So this is my P equals 1 atmosphere. And obviously, since the T2 is bigger than T1, that's why this is just sort of like, if I took the difference between those, it's kind of just a translation of those curves, albeit a volume-dependent translation because of the factor of gamma V over V. But because those are the only things that the only thing that has any temperature dependence is just the temperature that multiplies those, I would just get something that looks like this. And indeed, you can see that V1 is less than V2. So in some sense, that quote unquote explains thermal expansion. But I think, again, why is gamma positive rather than say negative or close to zero? It's because, again, materials really do have the tendency, well, I'll just go this way, materials really do have the tendency to, as you squeeze on them, their bonds get stiffer. There are interesting situations of materials where small ranges of compression have an effective negative gamma and therefore present a negative thermal expansion. Those would be materials that consist of large kind of chunks of things. This can happen for, I guess, cloth rates maybe sometimes. So you have like cages of atoms. And then you might have a situation where the material in ambient conditions has a lot of open space in it because you're packing these cages together. And then when you start to compress on it, you squeeze out the open space. And that might be actually very easy to do because you're mostly squeezing open space. And so in situations like that, then once you rearrange the things such that you have something more approximately closed packing of the atoms, then you get a positive Gruneisen parameter and you get back to the regime that's more expected of positive thermal expansion. But there are weird cases where negative thermal expansion happens, but only over very narrow ranges of compression and only for particularly weird looking materials. So that's actually all I had to say. I know that's not a very long solution set because I didn't give you very many or very difficult problems, but that's basically what I had to say. So let me see if you guys have any questions.
Thank you very much, Lorin. And the floor is now open for questions. There's only 30 of us here, so I would say let's see how the unmuting might work. So if you have a question, just unmute yourself and ask it. Let's see how that goes.
I have a question. So the conservation of momentum, mass, and energy came from the fluid equations,
Yes.
which typically have some assumption of the Knudsen number being very small. But if you go across a shock boundary, it's very, very short, sometimes nanometers. So how is it that we can use the fluid equations when the shock boundary can be so small and possibly small enough that the Knudsen number is large?
Can you remind me what the Knudsen number is again? I actually don't remember, but remind me what it is.
It's like the interparticle separation by the system size. So when it's large, I hope I've got this right, when it's large, you have very few particles in your volume and statistics don't work well.
Okay. Yeah, so what I would say is this. I don't think anybody, so thank you. I don't think that anybody would attempt to apply the Rankine-Hugoniot equations right at the interface between shock and unshocked material because of exactly the point that you're making. I mean, things would be a little weird there, and probably hydrodynamics is a little suspect. What I'm really envisioning is, let's say you are, a number of mean free paths behind the shock front, let's say, or in front of it, let's say on the other side. And that, I think that there's at least MD results do show that it's a pretty good approximation to use Rankine-Hugoniot in a situation like that. We're not really talking here about describing the shock front. That's a very different thing, and I don't think that simple things like the Rankine-Hugoniot jump conditions are expected to do that well. That's my answer. I'm not sure if that's really a good answer, and it might not even be the totally correct answer, but that's my gut feeling about that.
Thank you.
If other people have views about this, please, this can be a free-for-all discussion. I mean, I'd like to hear what others of you think about that, if you have opinions about it.
I'll take a crack at it. Rankine-Hugoniot really describes just the before and after, right? It doesn't concern the shock at all, only the material ahead of the shock and the material behind the shock. And it's really just making sure that conservation laws hold for that material, which is away from the shock. It's describing the delta, not what happens right there.
Right. Other questions?
I actually had a question which I think you answered. So I was going to ask you about the negative thermal expansion materials, and you mentioned cloth rates and open systems and things like that. There are, of course, some metals, that also have 0 or even negative thermal expansion invars.
Yes,
like
exactly.
guys.
Yes.
Do they have different kind of shock compression behavior than regular alloys? Because those invars come from the magnetic sort of moments. right? That's where they get their behavior.
Well, that's a good question, and I'm not sure I know the answer. What I will say is this, though: if I think about the materials for which that is true, and for instance, actually, delta plutonium, ambient phase plutonium, when it's alloyed with certain materials, it has such a negative thermal expansion, I believe, and certainly very close to zero thermal expansion. I think, the problem there is that a lot of those things are very close to ambient conditions. It's only like at very low pressures, and then you squeeze out the INVAR effect pretty quickly. And therefore, shocking a material like that, as you know probably better than I do, there's a question as to, you might not even be, I don't know what the Hugoniot-elastic limit. I mean, there's a question of what's the interplay between the pressure at which you'd squeeze out the INVAR effect and what the Hugoniot-elastic limit is. So there might be strong effects of strength that complicate situations like that, because again, the INVAR effect is something that's generally something that, if it happens at all, happens at pretty low pressures, and so it might be. I mean, much of shock physics concerns higher pressures. This is just, kind of what most people are interested in, and therefore you blow past a lot of that stuff. So it's really more just things that are buried in the initial state, but then you don't really study very much the negotiation of the transition. And if you were to study the negotiation of the transition, it would be necessarily confounded with understandings of strength and stress relaxation. So I don't know I didn't give you an answer, but I would say that it's complicated, at least in the few situations I've heard of that have INVAR effect type things associated with them.
Fair enough. Thank you. And congratulations on the Nature paper.
Oh, thanks. Yeah.
Other questions? Okay, well, Lorin, I think you've given us a lot to chew on. All of this has been recorded, so I'm going to post it on the YouTube channel hopefully within the next day or so. In the meantime, we've really enjoyed learning about this topic with you. Thank you very much.
I enjoyed it very much, and thank you very much for inviting me. As you know, I think I responded within 30 seconds of getting your email. I was very excited to do it. Yeah. Okay, well, goodbye, everybody, and have a great rest of the summer. And I will certainly be tuning in for a number of the subsequent lectures, because I want to learn this stuff myself.